We know that length is a one-dimensional measurement. For example, inches, meters, etc. We've spent some time looking at area. Area is a two-dimensional measurement. Even on a solid, area is still two-dimensional because it is a square unit. Inches squared, square meters, square yards, etc. And now finally we are at our last type of measurement, that of volume. Volume is a measure in three dimensions. It's a measure of space inside a solid. We can think of length as the distance, straight line distance between 2 points. We think of area as the amount of space covered in two dimensions. So think of movement on a chessboard, for instance, or a checkers board. You can go forward, backward, you can go side to side, but you cannot go up or down. So that's a two-dimensional measurement. You are covering an area. Volume allows you to cover in three dimensions. So you can go forward, backward, side to side, and now you can rise vertically and also fall vertically. So you have three different directions of movement. All those movements together allow you to cover a volume. And we think of volume as the space inside a solid. And more specifically, it's the number of unit cubes that can fill a solid. We said that area was the number of unit squares that comprised a polygon or a two-dimensional shape. Volume is the number of unit cubes that can fill that three-dimensional solid. Here's one example. I've outlined a prism in black. Cutting that prism into individual unit cubes would tell us how much space is inside that prism. Each unit cube would measure 1 by 1 by 1. So it has a volume of 1 cubic unit. And then if we cut that prism into several of those equal unit cubes, we see that we have 8 cubes going across here. We have 5 cubes going back this way, 5 cubes high. We could count all the cubes to determine the prism's volume. And just like with area, when unit squares didn't always work out perfectly, the same thing happens here. We can't fill this cylinder exactly with unit cubes. We're either going to be short or we're going to be over. So we have to look at some different techniques to calculate that volume, but the basic principle is still there. It just means that we will have partial cubes to cover this little space here and partial cubes to cover that space there. With a prism, it works out perfectly. With other things, it doesn't work out perfectly, but the concept is there. Looking at this example, we get a sense of what volume is as a calculation. If we count 8 cubes this way, we know we're 5 cubes deep that way. This bottom layer has 40 cubes. And if we have 5 levels, each level has 40 cubes, well, then it's just a matter of 8 times 5 times 5, which should be 200. 200 cubic units. There are 200 cubes in this prism. And that gives us a sense of what to do. We multiplied and found the area of this bottom level. And because all the levels are equal, we just multiplied by the number of levels we have. We took the area of a base. The base shape was this parallelogram or rectangle, and we multiplied it by the height of that base shape, or that solid. We would technically do the same thing here. Find the area of this base, which happens to be a circle, and multiply by its height, because a cylinder is like a prism. Every little individual level is exactly the same. It's as if we took this bottom circle and just copied it as we moved up and moved up and moved up to create one smooth solid. If we were to take a knife and cut horizontally, say through here, and then look down on the top, we would see a perfect circle. If I were to cut here, and this is what's called a cross section, where you make a horizontal cut and then you look down on top of what you just cut, you would see that base shape. Volume is nothing more than a base area times a height. And we're going to look at how to calculate volumes of the four solids we've already looked at: prism, cylinder, pyramid, and cone. And we also have one more solid we haven't looked at yet, and that's coming a little later on. Someday, some of you are going to take a calculus course. The second semester calculus, or sometimes it's called Calculus 2, you get to deal with volumes that are a little more tricky. They're a little more complicated. Volumes of these figures. These are what you would see more in the real world, because not everything is a perfect prism, pyramid, cylinder, or cone. They are all sorts of various types of curves and twists and shapes and whatnot. So calculus allows you to find the volumes of these different figures. And it's a little hard to see on this one right here. Let's see if I can blow this one up a little bit. You can see this little shaded part right here. This was a two-dimensional curve. I'm sorry, this was a graph, just some graph on an XY plane, and it was rotated, or revolved, I should say, revolved around an axis to create this three-dimensional shape. So just taking this two-dimensional curve and making it revolve around an axis created this 3D shape. It's still a base area times a height. Only now you're dealing with what's called a function, something like y equals 2x minus 1 or 3x squared plus 7. That's where the calculus part comes in and teaches you how to deal with things like that. Save this stuff for much, much later in your career, though. Start with the volume of a prism. Here's a prism. It's not standing on its base. It's lying on one of its lateral faces. And this is where it really becomes important to know what is a base and what is lateral, because we need to multiply the base area times the height. This figure here, this 60 by 80 figure, is not its base. Just because that's what it's resting on doesn't mean it's a base. We have to know our terminology. So if you need a review of that, go back and watch the video that introduces prisms, because you must know what is a base and what is lateral. Our base is this trapezoid. So the volume of this prism is the area of a trapezoid times the height of this prism. The height of the prism is the distance between the two bases. So in this particular case, base area times height. Well, our base is area of a trapezoid. 1/2 base 1 plus base 2 times little h for the area of the trapezoid multiplied by big H, height of the prism. This capital B represents base area, and here's the base area. This capital H represents prism height. Here's the prism height. Now we just plug in our values and solve. 1/2. The little bases, the trapezoid bases are 45 and 60. The little h, the height of the trapezoid, is 20. And the height of the prism is 80. Now we just have to punch all this together and then make sure we do a units check. Looks like it is going to be 84,000 cubic centimeters. Area is a square unit, and then we are multiplying by one more unit, and that's where the cube comes from. We are taking an area times another unit, which bumps that exponent up one more, which we also call cubed. One more prism example. Now our prism is triangular. Our prism is now triangular. So we have to alter our volume formula. Base area multiplied by height. Well, now since our base is a triangle, we'll have 1/2 little b little h, and then we have our big H. And again, notice the difference in the capital versus lowercase. Capital letter represents a base area. Capital H, height of the solid. And then the lowercase value, the lowercase letters, this is just the base of the triangle. This is just the height of the triangle. Our triangle base, our triangle height, our prism height. And it appears for this one we will get 94.5 cubic centimeters. For prisms, this V equals BH is a formula that works every time. Understand, though, that the B is going to depend on what shape you have here. If you have triangle, 1/2 little b little h. If you have a trapezoid, then you need to put in the area of a trapezoid. If you have a rhombus, you put in the area of a rhombus. Regular polygon, put in the formula for regular polygon, and so on. Capital B depends on what shape the prism's base is. For a cylinder, we know what the base always is. It's a circle. So cylinder formula will always be the same. Our base, our big B, is the area of a circle multiplied by the height of the cylinder. So now, again, we just plug in our values. And make sure we keep terms of pi for this one. 25,000 pi, and now we are in cubic inches. 25,000 pi cubic inches is the volume of this cylinder. Volume in a lot of ways is easier than surface area because, again, we are just taking this base polygon, this base shape, and we are just multiplying it by the height of that solid. That runs through the entire interior space. Think of volume as I want to fill this solid with something. Let's say water. How much space do I have inside? Surface area would be I want to paint this entire solid. How much space outside do I need to cover?